Thanks a lot, Natasha. I'll be talking about spaceKLIP today, which is our high contrast imaging pipeline for JWST that we have developed together with the JWST early release science team for the high contrast imaging of exoplanetary systems. And today I'm going to show you how you can use spaceKLIP to produce pretty images of exoplanets, such as the ones that you can see on the left-hand side here in these images, but also much more than that. So for our observations, we use a technique that's called chronography, and that's suppressing the light of the central star, which is why in those three images there you can't see the light of the central star, and we indicated the position of the star with this white star. But of course, in the middle of the images, you can see the exoplanet HIP 65426b that we've been observing with this early release science program, including the first ever image of an exoplanet in the mid-infrared at about 11 microns. All right, so here is a little illustration from Jeroen Leisenring in Arizona, who has also been developing a lot for spaceKLIP. That's kind of showing the concept behind chronography. So on the left-hand side, you have an astrophysical scene with a star in the center, and then you have in blue those two exoplanetary companions. And this black splotch is the chronographic mask. And as you see, as the chronographic mask is aligned with the host star, the raw image becomes fainter because you block out most of the light from that star. And if you do a reference star subtraction, which basically means that you have to observe a different star in the sky, which doesn't have any exoplanet companions, and you subtract that PSF from your science target, then you can actually see the PSFs of the planet, or both of the planets on the right-hand side. Now, what I want to point out is that even if the chronographic mask is aligned with the star, in your raw and unprocessed images, which you see in the center, they are still dominated by speckles from the host star. And that really motivates why you need a pipeline like spaceKLIP, or also the VIP tool that Valentin will be talking about in the next talk, to make the exoplanets visible in your images. So this is an overview of the spaceKLIP pipeline and what it can do for you. It consists of 5 different steps that are all making use of some other awesome open source software packages. The first 2 steps are used to reduce the raw telescope data with the help of the official JWST pipeline, with a couple of tweaks for high contrast imaging data products. The core of the pipeline is the 3rd step, which does the PSF subtraction with the help of the popular PyClip package. And then you have the 4th and the 5th step, which help you to better understand or interpret your data, your detection limits, and also to understand the properties of any detected companions. All right, so I'm going to go quickly through all of these steps and show you what they do and what they do differently from the official pipeline. So the first step is the ramp fitting step, which is basically taking care of detector level calibration, such as the dark subtraction or jump detection, which is trying to find some hot pixels or cosmic rays in your images. I mean, you can see here a comparison between the default pipeline and the spaceKLIP pipeline in the same scaling. And what you can see here is that the default pipeline is using quite an aggressive saturation correction, which flags a lot of pixels as bad that are not actually bad, that we found can be used for the further processing. And you can also see, if you look closely, you can see a lot of dark speckles in the image, which are hot or bad pixels from the dark subtraction. So the dark reference files that are being used are actually kind of noisy, and we found it's better to skip the dark subtraction step, at least for high contrast imaging, because you will get a cleaner product. There's also other things that we want to see. There's these background sources next to our target, which are known stars and not gravitationally bound to our target. But of course, we want to see them. We don't want to remove them. And then there's these darkish regions in the bottom corners, which are the neutral density squares that are used for the target acquisition process. And those are also real and not a kind of artifact. Another issue with the chronographic subarrays is that, at least for NIRCam, they're located in the middle of the detector, whereas the reference pixels, which are used to keep track of bias drifts and other systematics from the readout electronics, are located around the edge of the detector. So the chronographic subarrays, they don't have any reference pixels, which is kind of bad. So we added some pseudo-reference pixels around the corners of those arrays. And as you can see, if you follow how charge is being accumulated over time in one of the bright pixels in the center of this PSF, if we apply our pseudo-reference pixel correction, which is the bottom plot, then the charge accumulation happens in a much more linear and expected fashion. So we get a much better calibration. For the second step, we mostly improved the methods for the removal and cleaning of bad pixels. So this is a nice illustration made by Aaron Carter, who's also one of the main developers of spaceKLIP. And that's showing you the difference between the default pipeline and spaceKLIP again, and the way that we are cleaning the bad pixels. And this will be very important later for the PSF subtraction step, because for that you want to basically have an image that is as clean as possible of the bad pixels. And before we can actually start with the PSF subtraction, there's an extra step for the MIRI instrument, the mid-infrared instrument, because it was found that this has a very bright scattered light feature from the chronograph, which is called the MIRI glow stick. You can see it very bright here. It's scattered light of the 4-quadrant phase mask that is being used to suppress the light of the host star. And to get rid of that, you basically have to look at a blank region of the sky, and then you have to subtract that from your original science observation. And also spaceKLIP can help you to do that in the best possible way, and to actually make visible the PSF of your star, which is otherwise completely outshined by this bright glow stick. So then once we have our cleaned NIRCam and MIRI images, we can start to ask the question whether there's any planets in those images. And for that, of course, we have to do the PSF subtraction, for which we use the popular PyClip package that's been applied also for many other observations from the ground. If you're familiar with PyClip, you know that you have to construct your data cube of target PSFs and of reference PSFs. Again, it's a different star in the sky that doesn't have any companions ideally. You feed those into PyClip, which is doing the PSF subtraction with the help of a principal component analysis method. And then it gives you back the PSF subtracted image, where you can finally see the exoplanet that we were all looking for. Again, the light of the central star is suppressed here, so it's kind of not visible. You only see these dark black speckles, which are residual light from the host star. So we finally have our pretty picture of an exoplanet, but that's not where it stops. You can go further with spaceKLIP. It can help you to understand your detection limits. So one of the most important metrics in high contrast imaging is the so-called contrast curve, which tells you as a function of the separation from the host star, what kind of companions were you actually sensitive to based on the noise in your final images. And spaceKLIP can help you to compute that. Usually we express it in terms of contrast between the host star and the companion. Of course, the host star has been removed, so we can't really compute it easily anymore, which is why we have to use a model for the flux of the host star. And this is done using some photometry table that you can download from Visier for basically any star in the sky. So also very, very simple to do. Another issue with this principal component PSF subtraction is that it can also affect the flux of the companion. So this is an illustration that is showing, as we subtract more and more principal components using PyClip, also the flux of the companion of the exoplanet is kind of reduced. And it's a problem that we have to characterize in order to get the flux of the companion right. And for doing that, we typically inject fake planets into the simulations, and we run them through the entire pipeline, and we then check in the end what is the recovered flux and how much did it change from the injected flux. And spaceKLIP can do all of this kind of injection recovery process in a very systematic way for you, and help you to give this what we call the algorithm throughput curve that you can then use to calibrate the contrast curves and get the most precise possible answer for your detection limits. Then the last step is about any companions that you might have found in your images. Of course, in our case, we have HIP 65426b, and we want to know what is its brightness, what is its separation, what is its position angle with respect to the host star. And for that, we use again routines from PyClip and also simulated PSFs from the web PSF tool. We create basically a model scene of our observations. And using this model scene, we can then minimize the residuals and find the properties of the companion. And for that modeling process, spaceKLIP can also go to MUST and grab the most recent wavefront measurement of the telescope. So those measurements are done, I think, every 2 or 3 days. So depending on the date of your observation, we will automatically grab the closest in time wavefront measurement to get the most precise model PSFs for this kind of exercise. All right, so this is, again, the overview of what spaceKLIP can do. You can download it on GitHub. It's free to use for everyone. And we're happy to help you if you have any questions. Feel free to reach out to us. The cool thing is that you can really run each of those individual steps with only one line of Python code. So it's very, very easy to get started. On the other hand, there's a kind of a cumbersome configuration file, which configures all the parameters for the different steps. And if you want to go in there and tweak some things, it might become a bit more complicated, especially in the beginning if you're not used to the parameters yet. Another issue that we had with spaceKLIP was that it was developed under kind of a time pressure when the first JWST observations came out by many people in parallel, some of them working on MIRI data, others on NERCAM data, some working on Exoplanet, some working on disks. So I think we have now 10 different branches on GitHub that can all do some slightly different stuff. And we have to come up with a kind of a coherent way to combine all of this. And for that, we're also trying to shift a bit towards a different philosophy, which enables more flexibility for the user and kind of get rid of this cumbersome config file, but probably means to run each of these steps with not 1, but 5 or 10 lines of code. But as you can see, it's still a lot of work in progress. And we're also always happy for people who want to contribute. And with that, I'm just leaving you up with our press release images of the exoplanet that were made with spaceKLIP. I'm giving you the link of the paper in case you're interested, and I'm happy to take any questions. Thank you very much.
Excellent. Thank you so much for that wonderful talk. It was great. Do we have any questions? Oh, I do see Joe actually has his hand raised, so go ahead.
Hey Jens, that was a great talk. I just had a really quick one. Earlier on in your talk, you were showing the default pipeline and then the processed one with this tool. And it just looked like the two images had very different contrasts. I just didn't know if that was like an image artifact or if that was really how the process works. Yeah.
Yes, I guess you're talking about that, right?
Yes.
Yes.
Yeah.
So
So like just the background being so much brighter on the spaceKLIP.
yeah, that's because we skip the dark subtraction, right? So in that sense, we don't get as accurate of a photometric calibration, but we get a more clean image. And it's not a problem for us because we are considering in the end only the contrast between the star and the planets and not the kind of absolute photometry values that are returned by the pipeline. So for our use, we don't really care about skipping this dark subtraction. Of course, if you want to do some accurate photometry measurement, then this will be an issue, yes. But as long as you work on in contrast, then it's fine.
Awesome. Thank you so much.
Excellent. Thank you. Are there any other questions? Let me check. We also do have a couple of minutes so that we don't get too far ahead of our online schedule. So if there's any questions for any of the talks that we've seen so far this morning, please feel free to use the raise hand function and ask. Just to bring light to some of the questions that have already been asked in the chat. For Radek's talk, Joe asked about the not being provided a fitting routine and the reasoning behind this, to which it's to allow the users to explore different methods, to have a better understanding of the pros and cons of different methods.
I think Chris Stark has a question.
Oh, yes, I do just see the hand raised now. Go ahead, Chris.
Yeah, my question is for Jens. Jens, you talked a lot about spaceKLIP in the context of exoplanets, which is great. And you pointed out injection of fake planets to measure the contrast curve. I'm wondering if you could comment on how you might perform some of those processes if there is a disk in the image, in which case trying to detect the planet is complicated by the presence of the disk.
Yes, yeah, that's a good point. So right now, because we didn't have any of such observations for the ERS and the commissioning, we didn't really worry about that. So we don't have any specific functions to help you to get rid of the flux from the disk. I know there is some stuff already implemented in PyKLIP, some high-pass filtering, for example, that can help you to get find point sources in images where you also have disks. But at least for now, it's kind of left up to the user to make an own custom pre-processing step before trying to find the companions and extract their properties. But as we continue working on more data, which also has disks, as you know, we might update spaceKLIP and implement some more routines to do that in an easier fashion. Yeah. I hope that answers your question.
Yeah, thanks. It'd be great to see even things as simple as a high-pass filter in there to as a first pass, and removing the disk would be a really nice addition.
One quick clarifying question for you. You mentioned the VZA VOT tables as being necessary as part of the download. Is that part of the file that's currently up on EMAC for spaceKLIP, or is that a separate download?
So this is it's not part of the file that's on EMAC, because you basically, it depends on which star you observe. You just go to VZA, you download this table, and in the configuration file, you just say that's the path to the photometry table, and then things will work. Yeah, but we don't provide this table for every star in the sky. I mean, that's what VZA is already doing. It's kind of a big database. Yeah.
Perfect. Thank you.